At the end of this video, I hope that by using prefixes, you can name a binary molecular compound from its formula and write the formula of a binary molecular compound given its name. Chapter 7, Section 1, Naming Binary Molecular Compounds. Unlike ionic compounds, molecular compounds are composed of individual covalently bonded units, or molecules. Chemists use two nomenclature systems to name binary molecules. The newer system is the stock system for naming molecular compounds, which requires an understanding of oxidation numbers, and this system will be discussed in Section 7.2. The old system of naming molecular compounds is based on the use of prefixes. For example, the molecular compound Cl4 is named carbon tetrachloride. The prefix tetra indicates that 4 chloride atoms are present in a single molecule of the compound. The two oxides of carbon, which are carbon monoxide and carbon dioxide, CO and CO2, are named carbon monoxide and carbon dioxide respectively. In these names, the prefix mon indicates 1 oxygen atom, and the prefix di indicates 2 oxygen atoms. The prefix is used to specify the number of atoms, or sometimes the number of groups of atoms in a molecule, are listed in Table 7-3 on page 212 of your textbook or on the screen now. When naming compounds using the old system, or the prefix system, we can't use the double check method of using the charges involved to make sure we have the appropriate number of each species, because there are no charges involved. We are talking about telling the reader how many of each species there is. The prefix system. We say how many numbers are present. So for dinitrogen monoxide, we see that there are 2 nitrogens. Dinitrogen. 2. Dinitrogen. There's 1 oxygen, monooxide. We don't say monooxide. We kind of drop that first O. We just say monoxide if the name of the anion here is starting with a vowel. But that I'm not going to grade you down either way for that. Dinitrogen monoxide. We see a carbon. Notice that there's only 1 carbon, but we don't say mono in front of the first element. If it's a mono in front of the first element, we drop it. Just like we see over here in this PF5. There's 1 phosphorus. We don't say monophosphorus, we simply say phosphorus. If there's more than one of that first species, like in dinitrogen, yes, we have to say that. Di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And yes, you will be required to remember those. They're not very difficult, you're just counting to 10. But we see carbon surrounded by 4 chlorides. So we use the prefix that represents 4, tetra, carbon tetrachloride. Phosphorus surrounded by 5 fluorides, phosphorus pentafluoride. Now you can use the old system, the prefix system, for ionic compounds, much in the same way that you can also use the stock system to name binary molecular compounds, things that are covalently bonded together. Same rules. We have 3 of the metal, and the metal is going to go first. It's the least electronegative. So trilithium nitride. Trilithium nitride. Now you might be wondering, why aren't you saying mononitride? Because I've already indicated that there are 3 lithiums. I don't need to say nitride again. Because the less electronegative element is written first, oxygen and the halogens are usually given second, as in carbon tetrachloride and the carbon oxides. In general, the order of the nonmetals in binary compound names and formulas is carbon, phosphorus, nitrogen, hydrogen, sulfur, iodine, bromine, chlorine, oxygen, and then fluorine. The prefix system is illustrated
Further, in Table 7-4 on page 213 of your text, which lists the names of the 6 oxides of nitrogen. Note the application of the rule that states that the less electronegative element is listed first. Oh, too far. Covalent-Network Compounds. As you read in Chapter 6, some covalent compounds do not consist of individual molecules. Instead, each atom is joined to all its neighbors in a covalently bonded three-dimensional network. There is no distinct unit in these compounds, just as there is no such unit in ionic compounds. The subscripts in a formula for a covalent network compound indicate the smallest whole number ratio of the atoms in the compound. Naming such compounds is similar to naming molecular compounds. Some common examples are given on the screen now: silicon carbide, silicon dioxide, or trisilicon tetranitride. Acids and salts. An acid is a distinct type of molecular compound about which you will read more about in Chapter 15. Most acids used in the laboratory can be classified as either binary acids or oxyacids. Binary acids are acids that consist of 2 elements, usually hydrogen and one of the halogens, fluorine, chlorine, bromine, or iodine. Oxyacids are acids that contain hydrogen, oxygen, and a 3rd element, which is usually a nonmetal. Acids were first recognized as a specific class of compounds based on their properties in solutions of water. Consequently, in chemical nomenclature, the term acid usually refers to a solution of water of one of these special compounds rather than to the compound itself. For example, hydrochloric acid refers to a water solution of the molecular compound hydrogen chloride, which is HCl. Some common binary and oxyacids are listed in Table 7-5, which is on page 214 of your text. Many polyatomic ions are produced by the loss of hydrogen ions from oxyacids. A few examples of the relationship between oxyacids and oxyanions are shown on page 214 or on your screen now. An ionic compound composed of a cation and the anion from an acid is often referred to as a salt. Table salt, NaCl, contains the anion from hydrochloric acid. Calcium sulfate, CaCO4, is a salt containing the anion from sulfuric acid. Some salts contain anions in which one or more hydrogen atoms from the acid are retained. Such anions are named by adding the word hydrogen or the prefix bi to the ion name. The best known such anion comes from carbonic acid, which is H2CO3.
When aluminum metal is placed in a solution of 12 molar hydrochloric acid, the aluminum quickly combines with the dissociated chloride ion. In doing so, it forms a salt, aluminum chloride, and releases hydrogen gas. By definition, a salt is formed when a metal atom, or a positive radical, takes the place of the hydrogen of an acid.
Oxyacids are acids that contain oxygen. Now they have a lot of suffixes and prefixes that can change their name and can cost you points on a test. But there are some easy systems to remember and that can help you get the points that you deserve on the test. First, let's start with the most common version of a particular ion. For this example, we're talking about the chlorate ion. It is the ion that is formed between chlorine and 3 oxygens. Okay? and we see that as the central chlorine, and then it's surrounded by the 3 oxygens. This is called chlorate. Okay, we're going to start here. Now, when this chlorate ion, ATE, right? See how it's not chloride, it's chlorate, ATE. This is the most common ion. When it forms an acid, meaning we've taken that chlorate ion and added this hydrogen here, this acidic proton, aka acidic hydrogen, we replace the ate ion with ic acid. 8 becomes ic. 8 becomes ic. Now, if we have a chlorate ion that doesn't have 3 oxygens but has 4 oxygens, it's still chlorate ion, but we add the per in front of it, P-E-R, perchlorate ion. This is perchlorate. The per indicates that there's one more oxygen than the ATE, the 8 ion. Again, when we add this acidic proton here and it becomes an acid, the 8 becomes ic. So it is perchloric acid. So we have chloric acid, perchloric acid, formed from the chlorate ion, then the perchlorate ion. But if we actually go the other way, instead of adding oxygens, if we have them go away, notice here we only have 2 oxygens. This is the chlorite ion. The ITE indicates 1 fewer oxygen than the ATE ion. So this isn't Cl3, this is ClO3, ClO2. Now, when we add the acidic proton, the ITE becomes OUS, acid. So the chlorite ion becomes chlorous acid. We have chloric acid over here from the chlorate ion. 8 becomes ic. But from the chlorite ion, we get chlorous acid. Ite becomes us. Now, we can go a little bit more extreme. We can take that chlorite ion and get rid of 1 more oxygen. So there's only 1 oxygen here, ClO. Now we have 2 fewer oxygens than the ATE ion, right? The chlorate ion. We call this the hypochlorite. Again, ite becomes us acid. So this is as an acid. When we add the acidic proton, it's hypochlorous acid.
At this point, I hope that, using prefixes, you can name a binary molecular compound from its formula, and you can write the formula of a binary molecular compound given its name.